Okay, welcome back everyone. I think almost everyone is back from the lunch break, or if you're sitting somewhere in the US, God knows what midnight break you've just taken. But yeah, big thank you that you're still with us. Um, and now we're gonna go and have a look into mass spectra, so what we can do with the mass spectral information in terms of displaying and analysis, and we've got quite some funky things we can do there. And here it's really geared towards getting you from your data to something publishable as fast as possible. So essentially that you get a very nice display of concentrations you can compare between different volumes and so on and so forth. So that you get a display of the mass spectrum or of the mass spectral information as well as possible. But since we had some issues earlier, we will also revisit the mass spectral ranging just quickly, so that we can make sure that everyone's on the same page. I think also the ranged mass spectrum figure has been sent out to every one of you. Oh, bloody hell! Sorry, I totally forgot to take the pound sign out of the pound sign out of the post to table function again. Really, my bad. I will push that. I will push that straight away because that's like a 50-second fix. And I have pushed that change to GitHub. Sorry, that was really my bad. No, unfortunately not. It doesn't update the version on the FAQ page because that's a toolbox. And I think Valentin will just need to quickly repackage the toolbox. But that shouldn't take very long. That is really my bad. Okay. Yeah, so we'll just quickly go into the mass spectrum ranged figures, just that I can show you some of the things that you can get out of the mass spectrum figure if you need to work with it. Well, first of all, if you have newer versions of I should go back to here. First of all, if you have newer versions of MATLAB, what you can do is you can export the figure very easily as a vector graphic. So if you write a paper and you need to provide a mass spectrum, for example, it's very easy to just go here and export it as a vector graphic and just copy it in into Illustrator, Inkscape, or whatever vector graphics program you're using. And also showing, that your ion choices are quite sound by showing that the isotopic abundances are reproduced faithfully. And one trick I want to show you that we have put in is that if you have the selection tool on, so if nothing is selected here, and you click on one of the ions, then it will dump the ion's name into the so if you get the error that you have an invalid or deleted object, then your mass spectrum doesn't exist anymore. Either you have assigned the variable spec to something either you have not yet created the variable spec, or your variable spec refers to a mass spectrum that you have already closed. Okay. So yeah, what I just wanted to quickly show you is if you click onto one of these things here, you can see this is silicon oxide, this is silicon, this is chromium, and so on and so forth. So this is something you can pretty easily click on. And if you go on the selection mode, you can select certain objects. Yeah. So you can, for example, select this range here, this range here. You can select the text is not that useful, but you can select, for example, the stem plot. Okay, with the same color, it's a little bit hard to select. Now I've selected the stem plot of the ion, but I'll just show you what you can find in there. So if I go then I've made that range plot my current object. Do you all have the range figure open? Okay. And so in this object, I can dive as deep as I want. So you have the usual plot functions that you can use. So you can change transparencies, colors, and so on and so forth. But the most important part for us is the user data. And in the user data for a range, you have charge state, Hilt multiplicities, ions, and plot type. The plot type is, I think, pretty obvious. Let me just copy that in. So the plot type is, I think, pretty obvious. But the user data also contains the Hit multiplicities. In this case, it's defined from 0 to infinite. I think this was a question from Markus Kübach before. So yes, you can define them on certain hit multiplicities. We just haven't made much use of that. And you can also see what ion it is. And in this case, it's aluminium 27. And obviously, you can also go and look at the charge state. What you don't see here is the beginning and the end of the range. And the reason for that is that the beginning and the end of the range are implicit in the X data. So if I go O dot X data, let me just put that in a variable called test equals O dot X data. Then you can see we have the X data here, and it goes from 26.806 to 27.3806. Yeah. And this is where the actual range is. And I'll just put all of that in the chat as well. Oh. Sorry. Oh, it's not what I wanted. Copy. Oh, where's the chat gone? Paste. Yeah. And you can do the same thing. You can do the same thing for maybe an ion plot like this one here. And if here you go O dot user data, you will see that you have different options. So you have charge state, ion, plot type. And in this case, if I look at the ions, which is just in that answer variable, you can see there are 3 ions. First one is silicon 28, the second one is silicon 29, and the third one is silicon 30. So all of the information that you need to work with your data is in that mass spectrum. And Martina showed you can just easily save it. So if dot indexing is not supported for this, then you would be on a very, very, very old MATLAB version. No, that's not. Then you have not selected something. Then you have not selected a graphics object. If you have a graphics object, dot notation is definitely supported. So make sure that you have selected some graphics object. Yeah, so that you have selected maybe the range here or the range here. And I should probably go and say spec equals get current object. So one question: has someone that didn't have the iron find function work before now have the iron find function working?
I got it to work now, and I didn't before.
Okay, so the problem with the graphical user input is now gone. That's good. So let's just allocate the ranges then. Pause. Range exact for mass spec. And we wanna decompose. And because it's a relatively large data set, that will probably take a couple of seconds. What do you mean you don't see anything under iron find? You have to be a bit more specific, otherwise it's hard to help you. And now if I look at my pos variable, sorry, I know Martina always keeps them separate. I usually overwrite them. And so if you change ranges or anything, you need to redo that step again, okay? So if you change a range, obviously you need to reallocate the ranges. And here then we've got all the different things, all the different information displayed. For us, obviously, what's usually very important is what kind of atom or what kind of ion we're looking at. And this is actually what I call on a per ion information. And this is usually what we mostly use to determine concentrations and so on. What you will see later is obviously that we can also determine concentrations not on a per ion basis, but on a collective basis. So you have a variable with tens of thousands or millions of atoms in it, and then you can use additional information. For example, about ion overlap. For an individual ion, you need to make a decision of what that would be. But if you have a collective information, then you can do things like deconvolve and so on and so forth. And you will see that this actually, the basis for that is a very important foundation of what we do in our toolbox. And now, obviously, if I wanted to just see the, I don't know, aluminium doesn't make much sense. So maybe I just want to look at the chromium atoms in there. Then I can go and say pos dot atom equals chromium. And the chromium, this is under apostrophes because it's a string, and we want to have all entries from that thing, and obviously I want to put that into some kind of variable. Let's just call it chrom pos. And if I look into that now, then you can see it was a very easy thing to allocate that. And maybe, maybe I just want to see all of the chromium 52s. Yeah. Then I can go pos.atom x equals chromium and pos.isotope equals 52. Yeah. And now if I go into chromium pos, you will see we've only got chromium 52s anymore. Obviously the list got a little bit shorter. Yeah. And I could also filter by charge state. Yeah, this is all 2+. I think we've got chromium 1+. But essentially, I could do all kinds of filtering that way and all kinds of useful analysis. And this is really why we like working with tables, because it gives us a very easily visualizable way to interact with the data. Yeah. So all of the information that you have, you can just use to index into it. So for example, if you've got a digitizer-based detector, then you would be able to go and look at the peak heights or into MCP pulse heights and things like that. Yeah? So any information you have, you can just use and use it to filter, to do analysis, and so on and so forth. And the first obvious analysis that we might want to do is a concentration analysis. So we just want to see, okay, what is the concentration of the individual elements that we have in there. And for that, we can use the sorry, and I keep forgetting the names of all the functions, so I should probably have a list somewhere. Can someone help me out? So if you have an out of memory error, then the issue is that the memory that you have allocated to MATLAB is too small. Oh yeah, thanks. So it's pos calculate concentration simple, and we do that for the pos file. We do that for a detector efficiency of 0.37 because this gives us the the error bars, or the statistical error bars, statistical scatter error bars. And if we have allocated our ranges, this is all that we need to do. Okay. So if I then go into that concentration variable and if I go into that concentration variable, then I can see, okay, I have here a volume called pos, distance is 0, and these things will be important later. The type is atomic, yeah? It could be atomic or ionic. And then we have 3 different things. We have the count, we have the concentrations, and we have the variance. And the variance that's what we need the 0.37 for. And let me just pull up the help file. And there you can see we can also have an exclude list, and we can have a volume name. And so far you saw here the volume is called pos because that's the name I gave to the variable. But you might want to give the volume a different name. And why the volume is important will come up later, because once we plot the concentration, we can have multiple volumes that we plot into the same plot, and it will just compare the concentrations of the different volumes. So say you have 2 different data sets and you want to compare the concentrations that you have calculated, or you have 2 different regions of interest and you want to compare the concentrations, then you can actually do that by giving the volume the appropriate name. Then the next thing that we have is that we have an exclude list. And this means you can exclude certain elements from the concentration calculation. And that exclude list means that they will not be used in the concentration calculations. And usually the exclude list is especially hydrogen we don't want to include, and if it's FIB-based analysis, very often we don't want to include the gallium. And in this case, I'll just call the volume test, just so that you can see what's there. And you can see that the calculation is very, very fast. The reason why it's so fast is because it uses built-in functions that work on the basis of the categorical array that that we're using, that's behind the pos variable. So here, if you look into the atom section, this is a categorical array because here we have categories of the atoms. Okay. Obviously, you can go and change the categories. Yeah. So this is this allows you to do anything you want. And now that we've calculated that, again, you will see that the volume is now called test. There's still no distance because distances we only need for concentration profiles. The type is atomic. And here we've got the count. And you can see now we've got a count of 127,000 hydrogen atoms, but we have a concentration of 0. Because it doesn't go into our concentration calculation. And we have a variance of 0 as well. And we have the same functionality when we're actually plotting the concentrations. And I hope that makes sense so far. You can actually pretty easily do that yourself. So you can go histogram, pos.atom. Yeah. Oh, sorry. We need to create a new figure as well. It doesn't want to plot into a logarithmic figure. It's also a stupid idea to plot something into a mass spectrum figure. So I'll just create a new figure and plot the histogram in that figure. And what you see straight away is that we've got a histogram of all the different atom counts that we have in there. Obviously, since most of it is aluminium, this will be the dominant thing to display. So if you try to calculate the concentration and you have not allocated the ranges, then you will get an error. Okay, so you need to allocate the ranges first. It's very important, otherwise there is nothing to calculate the concentration from. At least not in this way of calculating the concentration. Okay, and if we have calculated the concentration, we can actually display it. And I will now open workflow the concentration, so that I can copy some of this out of here, and then we can actually plot our concentrations. And we have different ways of plotting that. So we can let's just go into the command line and help. Concentration plot. And you can see here that we can display the concentration with an exclude list. And in this case, we probably want to exclude the aluminium because it's a dominant element, and otherwise we just see aluminium. Then we can select a plot type, and obviously we also need our color scheme. So I will just copy that so that we have the full options here. So the concentration, that variable is already called cons. Then here we want to exclude the aluminium. Then as a plot type, we will start with a bar plot. And this color scheme is already variable is already called color scheme. Oh, sorry. And to display that, now I told him, okay, we want to have a plot for all three things. So concentration or count. Essentially, I gave him the concentration variable, and it is 3 entries. But really, what we want is we only want the concentration to be plotted. Yeah. So we want to have concentration with cons dot format being concentration and all the entries for that. And now what we get is a very nice plot where we can see, okay, we've got our magnesium, our silicon, our copper, our zinc, and we have quite a lot of unranged that we have in that one range that we call unranged. I have to have a look again where that one is. Oh, sorry. And we have a very large bar showing us all the unranged events. But we can also include exclude the unranged events. And now we get everything with just the elements that we're interested in. With this color scheme, obviously, it's a little bit unlucky. Magnesium and silicon are very close in color, but I could go into the color scheme and change it at any point and rerun the analysis. We have currently gotten 2 different types of charts. So we can have a bar chart and we can have a pie chart. Yeah? The default is bar chart. So if you don't write anything, you will get a bar chart. And if you write okay. Sorry, I just heard that there is a problem with the broadcast, and I know what the reason for that is. So let me just change that, and that should be gone now. Okay. So as I said, we have the ability to do that with a couple of we do the concentration plots a couple of different ways. And let me just create a POS file where we do not allocate. I'll just call it POS ions. In the POS ions, you can see we only we do not have the wait, did I what did I yes, so it should not actually be decomposing the ions. Thank you. This is why why it's a good idea. But we also have a POS undecompose. We can reverse the process. And now, so it's very good if people already know how things work better than I do. And now I can go, concentration is concentration calculation, and I use the pos ions variable, and if I do that concentration, you will see that we now have everything sorted by ions and not by elements anymore. This is obviously important if you want to do basic atom probe research, where you're more interested in which ions form where, rather than what chemical element they are. And you can use that also to then go and do the concentrations. Obviously, in this case, there's a couple of things I don't have in the color scheme, but the plot still works fine. Yeah. So now you can see how much water we have, how much OH we have, silicon oxide, and so on and so forth, compared to the other things. And it already knows, okay, the concentration is now in ionic percent. Yeah. And this will actually work for all different steps during the analysis, that it automatically will know that if you have an undecomposed, that you have a raw or just ion defined pos variable, that it knows that you want to do analysis with ions, and that if you have a atomically decomposed, that it will give you everything on a per atom or chemical element basis. Okay, I will just calculate everything then just for the regular decomposed pos file. And now I'll show you the comparison to, I'll just load in the superalloys dataset, just to have something to compare it to. And so now we can go pos superalloy equals pos to table. Oh, and it's a very, very, very large data set. So I might want to, I hope we have clipped that one, because the original data set is something like 150 million atoms or something like that. It's relatively big, so it might take a couple of seconds to get that started. Okay, so it's 30 million atoms, so it's not super bad. Yep. And I'll open the mass spectrum ranges. So you can see for the superalloy, obviously there's a whole lot of peaks that are there, but they're all nicely ranged. And I will just click now on the spectrum itself and go spec SA equals get current object, and do the same decomposition with pos SA. Spec SA decompose. And now I can calculate the concentration. Goes very quickly, and now we have another table here with the concentration. And this obviously contains quite a lot more elements than the aluminium dataset, because superalloys just consist of more elements than aluminium alloys usually. And now one of the neat things I can do is I compare the two. Obviously, it doesn't make too much sense to compare aluminium with a super alloy, but usually you might be compare 15 aluminium data sets or 20 super alloy data sets or whatever. But this is just to have an example. And for that, I'll create a new variable called concentration list, which is just simply an outer join of concentration and concentration SA. Outer join is a operation that allows us to combine the screen is out of focus, okay? So I can try and do it again with the without the optimize for screen for video option. So I think Annie London is actually correct there. That the problem might be that. So if you don't optimize for video, you always have this weird flickering black thing at the top. So I hope. Yes, I just sent the command. So the commands should be. Oh, sorry, I sent the commands to Martina privately. My bad. Obviously, all of you should get the commands. And so if you do an order join, then you get this concentration list where we have nans wherever there is no concentration. For example, the superalloy might not have manganese. And there are some undefined volume names. So maybe I should redo the cons SA and call it supra SA for superalloy, and the concentration as aluminium alloy. And then I can redo the concentration list, and now everything is a lot more ordered. Okay, it's a weird way it's arranged, but I think the outer join was the wrong one. Was the inner join. So usually I do that only with two. Okay, now it's 0. Okay, and now we all learn troubleshooting on the fly. Just join. Okay. That is now my failure. So now I've just used the So now I've just taken the aluminium data set and put the concentration in here twice. So usually you would mostly do that with the same, so with things that have to contain the same element or the same. The screen recording is still going, yes. That contain the same elements or contain the same things generally. So if I do that, I can do a concentration plot. Of why I just did a constant. Oh, my bad. So now I can do a concentration plot of the list, concentration list. And now what happens is that I get 2 bars. Yeah, and I can also move in the, so I can 2 bars because there's 1 bar for each copy of the concentration variable. So you now have to imagine we had 2 different concentration calculations from 2 different data sets. What would happen is that you would be able to see the different elements or the different data sets displayed in a row so that you can actually see what the difference is, the variance, and so on and so forth. So this is for the bar plots. And for the pie plots, we can go and change this to pi. And pi plot, obviously, you can only do for one single concentration variable. That anything else doesn't really make much sense. So you can see here, a pi plot also doesn't make much sense if we leave out the aluminium. Sorry about that. And the unranged. So we just delete that here. And then you can see a pie plot of how much stuff is in your, how much of what is in your is in your data set. And the reason why we've created these 2 options is because pie charts are usually very good for things where you have roughly equal amounts of each element and good for PowerPoint presentations. Whereas bar charts, bar graphs are usually very good for things where you have individual individual elements in smaller concentrations, and also great for publications. And again, you can always export this as a vector graphic or as an image. It goes very quick, goes very fast. One thing that I have seen, I have not merged in yet, is we also have the possibility to do stacked bar graphs. So a stacked bar graph essentially means that you can assign certain elements or certain ions that you want to have in one bar. So this is very nice if you want to look at stoichiometries or ratios. So for example, you've got a data set where you want to see, we for example had a data set where we wanted to see how much rare earth elements are in there compared to a certain, to lithium, I think. And so you have a stack, 1 bar where all the rare earth elements are stacked, and 1 bar with the lithium, things like that. Andy London says pie charts are good for nothing. Fight me. I hope, Andy, you know that this will be a pie fight, right? And I will be the only one to have pies, so it's going to be pie in your face. So I personally think pie charts are mostly useful for presentations, and especially for if you have roughly equal amounts of individual elements. But obviously, always with graphs, there is a wide range of opinions, and I think Andy London will have to watch out for me next time we meet, because I might have some pie on me. Pie is always great. Okay, so this is the simple. We called it simple concentration calculations, because all it does really is going into our variable, yeah, and just looking up how many atoms have been allocated to be aluminium, how many atoms have been allocated to magnesium, and so on and so forth. But obviously, in some cases, this is not really a good way to determine concentrations. For example, the superalloy is actually a very good example. Let me just open the mass spectrum from the superalloy, where if I go in and zoom into the mass spectral region here, you can see there's quite a number of overlaps. So this peak here, there's aluminium in there, there is probably chromium in there, there's probably iron. Yeah, so there's a whole number of peak overlaps there. And the problem with that is that we know that, and we actually can calculate from the isotopic ratios how much that would be. But we have not used that very often in atom probe concentration determinations. So usually if people have done that, they were like singular efforts, but they haven't really made it into widespread use. Actually for concentration plots like proximity histograms and 1D concentration plots, there's only one instance where I know that's been done, and that's Andy London working together with some guys with the guys from Oana Correa's group in Bochum, or sorry, Aachen, not Bochum, Aachen. Where they have used a concentration calculation program that did all the deconvolutions. Andy, can you say something about that? Maybe is that something? I hope I was correct in how I described it.
Yeah, I would say that it's in the software package ePOSA, which is developed by Jens in Aachen, and I'm going to talk a bit about overlap solving in the next class. So stay tuned for that. I'm not going to talk about proximity histograms.
Yeah, that's fine. Anyway, so I think in the future it's going to be very important to be able to write little programs that can make sense in a concentration manner, not just from individual atoms, but from collective POS files or subvolumes thereof. And yeah, Andy London has already done a very good job at that. And this is why we will obviously go and steal their code, because it's also in MATLAB. But that's why I want to show you a concept in MATLAB that's called function handles, or anonymous functions. And this is going to be important for us, because when we do concentration mapping, either in 1D, 2D, or 3D, we are going to be using those programs, and we call them concentration kernels. So you can write your own concentration kernel, just like the one that Andy London was just talking about, and you can plug it into any of our analysis downstream. Okay, and this is something that's very very important to us. And the way you do that is you create something that's called a function handle, and you can look up how that goes. So essentially, if we want to create a function handle, then we use that @ sign, and that denotes that we want to create a function handle. And then we can use some imports we want. So we can go, oh great, I'm on the German keyboard now, add concentration should be concentration at best post calculate concentration simple. And great, now I've lost my plot. Oh no, sorry, at x post concentration calculation simple x 0.37. Then we still want to exclude our hydrogen and gallium, even though there's no gallium in there, but you know, no harm, no foul. And we want to call the volume still, maybe we'll call it test 1. And what we've done now is we've created a function handle here that is actually to that concentration calculation function. So what I can do now is use that CK handle. So I can go concentration equals concentration kernel of pos. And this is actually exactly the same as we had up here. So if I go into cons, you will see we'll get the exact same result as before. And you might now ask yourself, why, how does that make sense at all? How can we, why would we do that? And the reason we do that is actually that now our function here is a variable. So I can go and pass this function into some other programs, and these other programs then can use that function to perform some sort of task. And for us, this task is usually creating a proxygram, or creating a 1D concentration profile, or creating a voxelization. And so what you can do is you can write a function, any kind of function, that takes any number of inputs, and as long as the output is consistent with our output here, with this concentration output here, so that you have a table that contains volume names, that contains names for the individual elements or ions. As long as you write your concentration function that way, you can then create this anonymous function, this function handle, such that it only takes pos as an input and outputs a concentration. And you can plug it into any of our 1D, 2D, and 3D analysis programs, and it will perform the concentration calculation according to how you wrote the calculation concentration program. So you can, for example, make use of isotopic abundances. You can make use of any information that you can think of, and it will still work with all of our downstream programs. We will actually go a little bit deeper into that when we look at ND analysis. And I think one of the most interesting things to do in this case would be to have a deconvolution concentration kernel, where we take the programs that Annie London and the guys in Aachen have written, and take that and create a concentration determination program that allows us then to have deconvolution in voxelization, so that your isosurface become more more accurate, or that our proxygrams take care of any deconvolution functions that we might wish to use in that case. with that, we're actually gonna stop with the concentrations here. And what I want to show you next, just quickly, is a little bit about is a little bit about spatial visualization. We're gonna mostly start spatial visualization tomorrow, but there's quite a few things to it. That's why it's maybe a good idea to take the couple of minutes that we still have left for the concentration calculation session to do that. Because we already had the functionality to do to display the mass spectrum, and we haven't yet looked into displaying in 3D. And in order to have a 3D display, we can just use the scatterplot pos data function. And here we want to display our pos file. The species we want to display, in this case, maybe silicon is probably good in something with precipitation in aluminium, silicon. And I should probably go with the help for that first, so that I can just go copy and paste. It's always the easiest thing to do. So you can see here, we will start with the simplest version of the plot function, or maybe we'll include the size already, the plot size. Okay, so there seems to be a bit of a problem with the broadcast. I'll see if I can make that a little bit better by just changing the options here. Is it better now? Okay, you might just have some black flickering on top of the bar. Okay, on top of the toolbar here. So apparently you can't have both at the same time. It's a bit of a nuisance. In the video, there shouldn't be a problem at all then. Later, okay? If you rewatch it. Okay, so let me just calculate all of the out of that. Copy, paste, so that you know how to use a concentration anonymous function. And here we want pos. The species that we want to have is, let's use two. Okay, let's use silicon, and let's use, what else did we have in there? Let's use chromium. I think there was some chromium. If there's no chromium, it will just be empty. So the sample in this case, we want to display all of them. So if you write 1, it means all of them. If you write maybe 10,000, then it means 10,000. If you write 0.1, then it means 10%. Okay, so anything below 1 is a fraction, anything above 1 is a number. But I'll try it with all of them. The color scheme is quite clear, and I'll leave out the size for now. And what we then get is a display of the atom maps. And they are linked. And you can see that chromium isn't particularly in the precipitates, it's just everywhere. Doesn't even show anything, any correlation with the pole structure here. Yeah, and this gives you a very nice way to display the data sets. So if you want to see all of them, you can just go and say, okay, the categories of pos, of pos.atom, which means because pos.atom is a categorical array, it has categories, and I have categories. Did I mistype something? Yes, that should work. Okay, I have no idea why I'm... Valentin, to have an idea what I did wrong, was there any change to the function that I might need to be aware of?
Unfortunately, I have no idea why it doesn't work.
But it should work that way, right?
I guess so, yeah.
So it's not just you people out there, it's also me, obviously, that occasionally runs into problems. Anyway, so
Maybe you try because the cell array it created is going horizontal and the cat cell array is going downward. So you need to take to, I don't know the English word, I'm sorry, to
transpose.
yeah, thank you.
I don't think that should be the issue. It was the issue. Huh, interesting. So if you do that, you get a display of all of the different elements we have in there. And you can rotate all of them and have a look which ones show structures, which ones don't show structures. Obviously, this is depending on the amount of screen real estate that you have. Yeah, whether that makes sense or not, I might just replot it with smaller dots. Oh no, that's not the one I wanted. And you can see it resizes depending on the size of your window. And this makes it really nice for you for any publications, because you essentially just need to adjust whatever angle you want. You can save it that way and then open it and either save the entire figure, or you can go on a per axis basis and export the graphics on a per axis basis. And what you can see is that we are now displaying essentially all of the atoms. So you can see this for a relatively large data set. And in the past, MATLAB wasn't actually that fast with the graphics system, but they have moved to a graphics system where they're really using the GPU to its full capability. And this computer has a very big, very, very expensive GPU. And you can see even with all of the atoms displayed, so really displaying all of the 23 million atoms, it still moves very smoothly and doesn't have much of a problem keeping up with the data. Okay, so the concentration session is obviously one of the simpler ones because we're only calculating simple concentrations. But we still have 20 minutes left in the session. And I think in this case it would be very good to go back to see where people got stuck and maybe take it up there again and revisit any problems you've come across. So in the new updated version that Valentin of the toolbox that Valentin has sent out, the problem with the pound sign has also already been resolved. And the problem with the people not having access to the get rectangle command, which I find rather curious because this is like an extremely simple command. Why would MathWorks restrict that? Anyway, I'll put it in the toolbox. Anyway, but this is resolved now. So I think it's a good idea to go through some questions. Who wants to start? Who is brave enough? Nobody. Okay, so since the most problems... Yes, Markus?
Yeah, I'm quite honest. So I was already stuck by the point where to load the spectrum from the figure. And it went, in fact, almost intuitive with you that you were clicking somewhere in the figure, and I got lost there with bugs. Later, I figured out that you just have to click
Oh yeah,
on the
fair
right
enough.
spec, and you're done. But that got me quite a bit behind. So yeah, I try to catch up, but it would be better next. In particular, in the beginning, when you need to click somewhere, that goes much slower. Because of the fact that it's not really so much clear. Now it's much better and clearer, but I really got lost already there.
So if I lost someone like Markus, then I've lost many more people. So essentially, if you reopen a mass spectrum figure, you need to have a variable somewhere. Or you're gonna need a variable that shows where the mass spectrum is, or that represents the mass spectrum. So it's a figure handle variable.
This is the one that you do with the assignment of GCO, right?
Exactly. Yes.
But the point is, I was clicking somewhere in the figure, and obviously in the wrong place. Um, and then I got just incorrect handle references, and then of course the downstream processing broke.
Yep.
So is it correct now that you can just click basically on somewhere on that black where the peaks are?
You need to click somewhere where you select the mass spectrum plot.
Okay,
Yeah. So
that's
you need to make sure that the mass spectrum plot is selected. If you move around, so the easiest, the safest way to do that is to just go somewhere where there's only noise, right? Because then you can make sure that what you select is definitely the mass spectrum and not.
yeah.
In this case, now I would have the axis selected, or the box or the legend or something like that. You really want to make sure that it's the mass spectrum that you have selected.
Yeah. And now it's clear, and one can catch up
Yeah.
on this one.
And
But
then
but this is the typical intuitive things for people immediately got lost. I at least got lost.
yes, and I'm sorry for that, but if someone like you got lost, then I assume a lot more people got lost.
That's humbling, but I think there's no specificity. I'm always slow with these kind of tutorials.
Yes.
But that's a side note. No, thank you.
So Martina just wrote, if you're lost, just ask the host or a co-host if they can help you.
Thank you. Yeah, great.
Yeah, Florent, you've got a question?
Yeah, so I still haven't been able to sort my problems. So basically, for the last 1 hour or so, I didn't follow any of the instructions. I was just wondering if maybe after the workshop you would answer some questions
yes, we can definitely do that. I was thinking to probably do weekly updates in the same format as we have now, because we are obviously also going to be adding more functionality, especially when it comes to interface analysis and the like. And so it's probably good to just have a fixed hour every week where we can go through questions and also introduce new functionality. Is anyone apart from Florent that could not open the MATLAB live scripts at all? Because the problem with Florent was that Florent really couldn't open it at all. Okay, everyone apart from Florent could at least open. Okay, David, you couldn't open it either. What error? Can you share your screen maybe? Okay, so if you have undefined functional variable tile layout, then you're definitely on an older version of MATLAB. So the tile layout was only introduced last year or the year before. Okay, 2028 should definitely be there. Okay, so there's a couple of things that the live scripts I think were introduced in 2017 or something, and the tile layout I think sometime last year or so. So there hasn't been a MATLAB for all that long. But it does have quite a lot of upsides compared to the older version. Okay, it was introduced in 2019B. Okay, so relatively recently. So Florent is asking if there might be a problem because he's not admin on his computer. I don't think so, because I'm also not admin on the computer I'm working on here, and it's still working fine. And it's still actually working fine. So I don't think that should be the issue. So everyone else was able to catch up with us and to do everything properly? I heard one yes. That's already very, very nice. That makes me very happy. So the videos, I will put the videos just on my YouTube channel. Okay, so Dave Reinhardt got through it. Okay, that's very good. But Dave's already a pro. 85% is already very good as well. So we just need to make sure that when we move to the next things, that all of you. Okay, so the problem with the memory usage. So MATLAB. MATLAB has so MATLAB runs in Java. Okay. And so Java is essentially no. Reduce memory requirements. So if you type memory, it will show you what kind of memory you can, what kind of variables you can get in your MATLAB generally. And if you have a computer with a relatively small RAM, It might be that the amount of memory that is allocated to Java and to MATLAB is too small to load something in. So if you have a very large atom prop dataset, and the ones we were working with so far, they were actually not that small. 20 million, 30 million atoms is not that small. If that's something that that exceeds the memory allocated to MATLAB, it will not properly work. How large would you suggest? It depends on how large your datasets are. If your datasets are all just 1 million atoms or 5 million atoms, you probably can get away very easily with a 4 gigabyte RAM machine. Unfortunately, I don't know how much bigger MATLAB itself has gotten. But back in the days, I had a laptop with 4 gigabytes of RAM and it worked fine on most things. The problem is once the size of memory, the memory you need becomes larger than your RAM, MATLAB will go into swap space. So it will start using your disk as RAM. And this is incredibly slow. And this is where the slow loading times come from. So right now here on the PC I'm on here is an 8,000 euro PC. So this has I think 96 gigabytes of RAM and a 2,500 euro graphics card and all of that. So you can load in 50 atom probe datasets and have no problem at all. But if you are on a machine with a very small memory, and the problem here is very often that you may have a machine with 8 gigabytes of RAM or 4 gigabytes of RAM, and Windows 10 is already very big. Yeah? So the operating systems have gotten bigger and bigger. So the operating system is taking up more and more of your RAM. So you're having less and less space to work with MATLAB or any other data analysis programs. And you can see that the maximum possible array that you can get on your machine is 73 megabytes. Oh no, 73,000 megabytes? That sounds a bit much. Plus 10 bytes. Memory available for arrays, 73. So you have 73 gigabytes. Okay, Andy London also can't open the live script. That's a weird one. We haven't had that one so far. If you have 80 gigabytes of RAM, you should not have a problem at all. So some of the work that I do on a machine with very, very large RAM, because it allows me to work on 100 data sets at the same time. So I'll show you on Friday how to work with large numbers of data sets. But in this case, having a lot of RAM is obviously very helpful. I think everything larger than 8 gigabytes should be fine these days. So 16, 32, and this is usually what you have on any kind of laptop or PC anyway. So we still had one. You got lost. So Cynthia Rodenkirchen got lost on the error post allocate range. Dot indexing not supported for that kind of for variables of this type. Okay, that's a weird one because dot indexing is definitely SA is post allocate range. Okay, so your spec SA is obviously not a graphics object. So when you open the spectrum, and I can just do that for you again. So when you open the spectrum and you loaded it in, you might have clicked on one of the ranges or one of the ion plots. Yeah. So if you go somewhere where there's nothing in the vicinity, then you can be relatively sure that what you click at is actually the mass spectrum. And if you then go spec SA is get current object, then you should be able to go spec SA dot and then you will get some autocomplete. So there's obviously some dot indexing happening here. Can you try that for me quickly so that we can have a look at that? You can also share your screen if you like. Or have we already lost you, Cynthia? Okay. Maybe also you can start chatting to one of my colleagues like Martina or Benedict or Valentin, and they will also be able to just help you out one on one to just make sure that we don't lose you along the way. Okay, with that, we're actually at the end of the session for the simple concentration calculations. And we'll have another break. And after the break, I'm looking forward to actually Andy London taking over. And Andy London will actually show us a little bit more about I think concentration calculations. And do you also show us something about crap? I keep forgetting the name of the library.
Sorry, it's too generic. It's Atom Probe Lab.
Atom Probe Lab, thanks.
It's like MATLAB,
Yeah.
but it's Atom Probe Lab.
Yeah, well, Atom Probe Toolbox is also not too specific, right? It's also fairly generic. So it's not like our naming scheme is any better here.
Yeah, we're gonna have a look at composition uncertainty, primarily revolving around peak overlaps, because that's peak identification is kind of a big deal, and I'm going to go through some of the tools in Atom Probe Lab, sort of in general, and some more specific things, and yeah, try and demo some stuff live as well using a live script. I sent an email. Let me. I assume everyone got that, but let me post it in the chat here as well. So if you can, during the break, if you could take a second to go to the SourceForge and download the latest zip file. And I don't have it packaged, so you just get a zip file from me. That's it.
So Hazel, what did you get? Did you get the lectures or did you get the data from Andy?
Beg your pardon?
Oh no, Hazel just wrote that. I got it. Come on, Hazel, you could have just said no. I got everything.
So for the most part, I'm not using any actual data. It's all either simulated data. So that's one of the tools, is the mass spectrum simulator, and there's a tiny POS file which we can use that's embedded in Atom Probe Lab.
Okay.
Anyway, go and have a break.
Yeah, so we're gonna have a break, and I'll see everyone in 15 minutes, and then we'll start with Andy.
Cool. See you then.
And I've just decided I will stay here in case people have questions that they were too afraid to ask early on. Yeah, so what I really hope we're going to be able to do in the future is to use some of the code that Andy has written to really deconvolve mass spectra and integrate it as well, so that we can have concentration kernels that do all the heavy lifting concentration deconvolution work for you. I believe that Kamika already has done something like that. I've read a recent paper by you guys, is that already in Atom Probe? Is that already in the AP Suite 6, or is that something that it will come in the future?
What exactly are you asking about?
So the Bayesian estimators for the concentrations.
So that